All right, everyone. Great to have you here. So as you know, today we're having a bit of a special session, and it's my great pleasure to introduce to you the host for the day, Andrei Gomberg. He's a professor of economics at ITAM in Mexico, and he was supposed to be chairing the 15th meeting of the Society for Social Choice and Welfare, which was meant to end today. I think we would have just gone to the first few sessions of the day. So Andrei, over to you.
Thank you. So yes, thanks to COMSOC for organizing this. So it's not just me. So Kanishka is present here, David Cantala and Diego Dominguez, the other co-chairman. We were supposed to have been welcoming you to the Palacio de Minería in the very center of Mexico City, which would have been a wonderful conference. We still hope it will happen. We still hope it will happen next year. We've fixed the dates so far, subject to all the uncertainty that we're facing right now. September, provisionally, things are fixed for June 23rd to 26th next year. So exactly a year from now, we hope to welcome you to Mexico City. We're planning to restart submissions on December 1st. And if you would like to continue with whatever you've submitted, those of you who have submitted, we will consider that. Otherwise, you know, everybody is welcome to submit, and we hope really this is going to happen. But for the moment, we're in this format we're all just getting used to still. So today's session will start with a presentation by Leeat Yariv, who was supposed to be one of our plenary speakers in Mexico City. So with not to waste time and without further ado, Leeat, so she's at Princeton, and I presume you're in New Jersey right now. Yes. So welcome, let's start.
All right, super. Thank you so much, Andrei. It's a real honor and pleasure to be here. So what I'll tell you about today is a paper about allocation with diverse preference intensities, which is co-authored with my colleague Pietro Ortoleva and one of our stellar students, Evgeny Safonov, who might be on the market next year if there are any jobs to be had. All right, so what we're focusing on in this project are allocation problems, and those are very prevalent. So you can think about public housing that's allocated to individuals, school choice, where students choose schools, appointment scheduling, either with doctors, for example, or even with us as faculty, with students, food distribution to the needy, and so on and so forth. Now, often in many of these examples, agents actually agree on the ranking of the goods. So, for example, most students would prefer a higher ranked school. However, they vary on how much they care about it. So, in other words, they vary in preference intensity. In addition to that, in many of these examples, there are no transfers, either by law or by repugnance or what have you. So the main questions in this project are, first, what's the optimal way for a social planner to allocate services? And related to that, if they don't actually observe the preferences of individuals, how can they elicit them in an incentive compatible way? So in other words, what is the optimal second best or constrained efficient allocation here? So these are the two questions I'll focus on in this short talk, and I'll jump straight into the model because of time. All right, so here is the simple model. I'll describe it more generally, and then I'll restrict attention even further to a particular example so that I can show you the main results. So there is going to be a continuum of goods. So it will be denoted by 0 to t, for instance, where t is greater than 0. And that can stand for schools that vary in quality, or public housing that is provided at different times, or doctor appointments that vary in the physician's expertise or the date in which they're provided. There's going to be a supply of these services that's going to be captured by a density function f of t. So f of t has a support on the set of goods, 0 to t, and a cumulative distribution function, capital F of t. So again, this little f of t stands for the supply of housing or food or appointments and so on. Now, with respect to agents, I'm going to focus only on two types today. So there are going to be two types of agents, P and I, with masses mu P and mu I, which are strictly positive. And they're both going to have a utility over the set of goods. And what we're going to assume for simplicity is that this utility is decreasing on 0t. So in other words, the ordinal ranking is the same for everyone. Everyone thinks that 0 is the best and t is the worst. So without loss of generality, we're going to normalize the utility at 0 to be 1. Now we need to capture somehow this idea that people vary in their preference intensity. So a natural way to think about it is that people vary in their marginal rates from getting a superior good. So the way we're going to model this, as it turns out, it's very useful to think about absolute risk aversion. So naturally, you're going to have some criterion that depends on the curvature or the marginal features of these utility functions, and we'll assume that the P agents are effectively more risk averse than impatient agents. So one way to think about it is that you have a set of goods, and one person, say the prudent person, is more risk averse than the imprudent person. There's a demand for a single indivisible good, and the outside option has a value of 0. So this setup captures many things. So in particular, I just mentioned the varying risk aversion, but what I'll talk about actually today is a different type of example where you actually have identical goods that differ only in their delivery times. So this might be the case, for instance, for public housing, if you thought that the units were fairly similar and just provided at different times, or appointments with your students where it's always you who are meeting them, but you schedule them at different times and so on. So we normalize the good at value at 1, and then the P agents are now the patient agents who are going to have a discount rate of RP, and the impatient agents or I agents will have a discount rate of R sub I, and they'll have the standard exponential discounted utility. And the patient agents are indeed more patient than the impatient agents. In other words, their discount rate is lower. Okay? So this is the example that I'll focus on today. All right, so the last component that I'll need to describe to you some results are what time lotteries and allocations are. So a time lottery is just a distribution over the set of times of these appointments. So Q of t will correspond to a density function that just describes what's the probability that you get the service at any time t. The expected payoff is then just the corresponding expected utility that you get. So you just discount the value of the good, the probability that you get the good at time t with the appropriate discount factor. An allocation will then be this pair. So we'll need to decide how to allocate stuff to the patient agents and how to allocate stuff to the impatient agents. And we'll have one constraint, which is feasibility. So recall that f of t was the supply of goods at any time t. We can't give more goods than we have. So at any time t, we need to make sure that the amount we give is not more than the amount we have at time t. So that's the feasibility constraint. And for today, I'll assume that there is sufficient supply. So in other words, with all the supply that you have for all the times available for you, you can satisfy all of the consumers. Recall that mu p and mu I are the masses of patient and impatient agents. So again, the expected payoff is just a discounted utility, and the welfare criterion, or the objective that we'll consider today, is just a standard utilitarian welfare where you weight equally both types of agents. You could also weight them unequally. I won't really talk about it today. Nothing really changes. All right, so I'll start by describing to you the optimal mechanism. So in the optimal mechanism, what we assume is that agents' discount rates are actually observable. So you know exactly the types of agents that you're facing. That's relevant for some applications. Well, sometimes you observe the urgency of appointments. So for example, you know that your students have some upcoming deadline, or we might see some health proxies for individuals who are waiting for food or for medical service and so on. All right, so what governs the decision of what goods to allocate to whom is the benefit of allocating to a patient agent relative to an inpatient patient at any time t. Or in other words, this function g of t that captures the difference. So this function just captures the difference between giving the good at time t to the patient agents or the inpatient agent. So the general idea is that you want to serve the inpatient agent when this function takes very low values, and you want to serve the patient agent when the relative benefit of serving them is high, or in other words, when this function is high. Okay, so now let's think a little bit about this function. So at 0, this function takes the value of 0. So intuitively, we're going to serve the inpatient agents initially. But it's single peaked. And just intuitively, if you take t to infinity, it also goes to 0, this function. In between, it's positive, and you'll need to believe me that a caricature of it is something like this. All right, so now let's think about the optimal mechanism. And for that, it will be useful to think about two particular times. The time t bar is the minimal time at which you could serve absolutely everyone. Okay, so that's the time at which you serve absolutely everyone. And t sub I is the minimal time from time 0 that you would need to serve all of the inpatient agents continuously. Okay. All right. So now when do you serve all of the inpatient agents first? When the costs are low, up to t sub I. Formally, when the value of the function at ti is lower than the value of the function at t, so again, the value of the function when we can supply all of the inpatient agents is less than the value of the function at the time at which we could supply everyone. So let me show you in pictures what it looks like. So this is a situation where ti is right here, so we could satisfy all of the inpatient agents in this region, and then t bar is over here. So in other words, this is the region in which we would supply all of the patient agents. And notice that the value of the function here is lower than the value of the function at t bar. And so what it means is that the value of serving the patient agents over the inpatient agents is higher in this region, in the green region that corresponds to service of the patient types, than in the region in which the inpatient types are served. So that kind of makes sense. That's what we want to do. We want to serve them when it's more valuable to them. Now, it doesn't have to be that this mass of the patient types is fairly small. So you could also have cases like this, where still the region at which we're serving the patient types generates a higher payoff, a relative payoff for them than the region in which we're serving the inpatient types. Okay. All right, so when do we serve inpatient agents with a quote unquote lottery? So by a quote unquote lottery, I just mean that they're being served over discontiguous intervals of time. So either they're served very early or they're served very late. Well, that's the case when the costs are high around the time at which we could serve them all. Or in other words, when g of t sub I is strictly greater than g of t bar. So let me show it to you in pictures. So think about the situation as such, where at t sub I, if we were serving all of the inpatient agents first, the value of the function is higher than a t bar when we complete service of everyone. Then intuitively, here it's very costly to serve the inpatient agents because the benefit to the patient agents is very high. So what you could do is shift a little bit of weight of the inpatient agents from around here, from around t sub I to around t over here, right? And this would help because the function g here is lower here than over here. So such a little shift would generate this pattern of allocation. And you see still that the value of serving P agents here is lower than serving them over here. So you could continue shifting weights to the end of the inpatient agents till we reach a point at which the value of G is precisely the same at the two ends of the interval at which the patient agents are served. Okay. So this will be the optimal allocation, and it's characterized by two restrictions. The first one is that we can no longer have any beneficial shifts of the impatient agents. So this is sort of an analog of a first order condition, and we want the function G to coincide at the two ends of this interval. The other restriction is a feasibility restriction because we have to satisfy all the patient agents in between these two times. So these are the two restrictions, and this is the first proposition. So I won't read all the details of it, but you see here the two restrictions that we have on the intervals that constitute the optimal allocation. Now, the shape of G guarantees that, in fact, this is unique. The optimal allocation is unique. And so we conclude by saying that the optimal allocation effectively has two possible shapes. Either we serve all of the impatient agents first and then the patient agents, or we serve the impatient agents with a quote unquote lottery. They're either served in the beginning or at the end, and all the patient agents in the interim. All right, and this is just I don't have time to talk about comparative statics, but this is basically what it looks like for the special case of a uniform supply. It will generally looks like this. So this is just a figure of the structure of the optimal allocation as a function of the two discount rates. The patient agent is on the x-axis, the impatient agent is on the y-axis here. All right, so now let me move to the second best allocation. So in the second best allocation, you want to allocate services when urgency is not observed. So this is relevant for many settings. So for instance, when you think about public housing, the family circumstances that led people to seek public housing might be difficult to observe. The urgency and need of attention and scheduling is sometimes hard to observe, both in the medical context and also in our academic context. So the designer is basically facing a standard screening problem here. So I won't go through the details of the formal problem, but for those of you who want to see it, I put it on the slide. But intuitively, what you want to do is maximize the same welfare that we had before, the utilitarian efficiency, now subject to incentive compatibility and still the same sort of feasibility that we had before. So incentive compatibility here essentially means that no type wants to imitate the other type and get their allocation. That's incentive compatibility. All right, now the first observation is that if you have an allocation in which all type K agents are served before all type M agents, that can never be incentive compatible, because those who are served later would always want to emulate those who are served earlier. So in other words, our allocation that serves the impatient agents first and then all of the patient agents can never be incentive compatible. The patient agents would want to imitate the impatient agents. So at least one of the types has to face a lottery. Now, as it turns out, this opens the door to potentially having the second best coincide with the first best when it involves a lottery. And in fact, proposition 2 tells us that for a positive measure of discount factors, the first best allocation here is incentive compatible. How about the general case? I won't have time to go through all of the details, but let me run you through an example just to illustrate what drives the full characterization. So just to fix parameters, let's think about a situation where we have a uniform distribution of supply over time, and there is an equal mass of patient and impatient agents. And let's fix the discount rate of the impatient agents at 1. This is arbitrary. What I'll do now is just show you a bunch of pictures that correspond to changing the discount rate of the patient agent, which is naturally lower than 1. All right? Okay, so let's start from a situation where the patient and impatient agents are actually fairly close to one another. What you see on the top is the optimal first best allocation that we just characterized. And as it turns out, it involves a lottery. Now, in this case, as it turns out, because the discount rates are so close, the impatient agent is actually envious of the patient agent. They would prefer their allocation. So in the second best, what do? We make the impatient agent's allocation a little bit better. So in other words, we shift the patient agents a bit further in the future and provide the impatient agents a bit more of the service early on. Now, as we decrease the patient agents, we're exactly in the realm in which the second best coincides with the first best. So this is a case in which the patient agents are happy because they care about the future, and for them it's quite meaningful to have delayed service. The impatient agents are sufficiently more impatient that for them, the value of getting this good early on overwhelms the fact that they're paying some cost by potentially having a delayed service. So both types here are happy, and we have the first best coinciding with the second best. Now, this is what happens as we decrease the patient agents' discount factor. We make them more patient. In the optimal allocation, naturally, the region in which they're getting service gets delayed because they're more patient. And that suddenly, at some point, makes their incentive compatibility constraint bind. So at some point, they're going to be envious of the impatient agents. So what do? Well, we make their allocation a little bit better. So we shift their service a bit forward relative to what is optimal. Yeah, and that is what will happen. Now, as we decrease the patient agents even further, we have two considerations to take into account. So the patient agent's incentive compatibility constraint still binds for the same reasons. So now we can push their service even further to earlier times, or we can make the impatient agent's allocation less appealing. How do we do that? By delaying service for them. And at some point, for the impatient agents, actually, whatever they get in the far future is not very meaningful. If you're very impatient, at some point, delayed service doesn't matter for you. So you may as well punish them very harshly. So in fact, as it turns out, in this problem, whenever you delay service, you're going to delay it to infinity for the impatient agents. Or in other words, you're going to just dispose of services. And in fact, you might even get full delay. So at some point here, you're getting the impatient agents only receiving service in the beginning or not at all. And it continues like this as we decrease the patient agent's discount factor. So in other words, we get a picture that looks something like this. So again, this is a picture of the second best allocation as a function of the two discount rates. And what you see is that it always has the structure of the impatient agents being serviced first, and then the patient agents, and then the impatient agents being served either in part or in full. So these yellowish, mustardish regions correspond to a delay, and here we don't have a delay, and the turquoise region corresponds to the first best, coinciding with the second best. So as it turns out, our full characterization essentially echoes this figure. So the second best allocation is unique. It's fully separating. In fact, it's fully separating star because the patient and the impatient agents have no overlap in their allocation. So it's even stronger than standard separation. And it belongs to one of the 5 classes that are described in the figure. So just to highlight kind of the 3 components here in this figure, there are essentially 3 things you need to prove, and I won't show you the proof, but if people ask me questions, I can show you some intuition. So first of all, there's no wrong spreads. So the impatient agents are never served between patient agents. The patient agents are always served in one block with no intermittent delays, so they never experience delays. And whenever there is delay for impatient agents, it's indefinite. So before I end, let me just show you in one picture. This is the structure of the second best allocation, the optimal constrained allocation. And we still have feasibility. So we need to satisfy all the patient agents in this region, which notice means that we can connect T2, this threshold, to this threshold. So in other words, the supply function gives us an implicit relationship between the two endpoints. In other words, in finding the second best allocation, we essentially have 2 degrees of freedom. So this time T1 controls the distribution of early service between agent types, while the time T3 controls the service probability for the impatient agents. So if T2 equals to T3, we don't serve them at all, and otherwise we serve them at least partly. So that's the conclusions. So lotteries might be useful. The first best allocations may also be the second best allocations, and artificial delays might be useful in this setting. That's all, folks.
Thank you. We have several questions. So should we just go in order of who asked them? So Peter van Emden?
Yes. I was wondering whether the result you had in the first theorem was fully dependent on the precise algebraic nature of this function g, or whether it's just a consequence of its convexity behavior, behaving somehow like a parabola, having a single maximum and being twice differentiable continuous.
Yeah, so for the precise result, for the structure of the lottery, the fact that the impatients are serviced before the patients and then impatients, all you need is the single peakness, or in other words, concavity. But in general, the entire construction could work for any arbitrary function. So I'm basically giving you a prescription of how to identify the optimal allocation, right? So essentially you want to make sure that you're satisfying the patient types when this function takes the highest possible values. So even if it had a wacky shape, we could use the same sort of techniques to characterize the optimal allocation.
Thank you.
So the next question, I think, is Reshef.
Yeah, can you hear me?
Yes.
Yeah, so I was wondering if like same model or similar model can work for allocating space, like parking slots. Suppose, you know, everyone wants to park close to the office building. There's one building, everyone wants to park close, but some people are okay with walking a little bit, others are like the impatient one.
Yeah, in principle, yes. So the only restriction to get the full characterization, if you want really this IPI structure, you need some structure on the utilities, right? So we can't do it with no assumption whatsoever. And for us, the absolute, as it turns out, this ranking of absolute risk aversion is the right one to generate all of these results. So if that's an assumption that holds in this application, then absolutely. If it doesn't, like I just answered Peter, you could still use the same sort of techniques. The optimal allocations might look a little bit different, but you could use the techniques.
Thanks.
We have at least one more question, Jean-Francois.
Yes, it's a very cute model. So the question is, to what extent it is really a magical property of the ordered two types, and so the question is, what about more types?
Yeah. So let me show you some slides on this. Let me just find them. So some things remain with n types and some things don't. Okay, so let me, whoops. I'll share the screen and I'll show you some stuff. So you could think about n types. So for example, just I kept the slides with the discounting example. It needn't be discounting. So the second best allocation, we can still show that it's unique. It exhibits full separation star, so different types will be served with non-overlapping intervals. And this is something I didn't really talk about, but we know something about the structure of incentive compatibility constraints. So for example, in our setting, we can't have both incentive compatibility constraints bind simultaneously, and this is effectively the analog of that. But new phenomena can emerge. So you might actually get kind of quote unquote wrong spread. So this is just an example to illustrate to you a case with three different discount rates. And this is a uniform distribution, of a triangular distribution of supply. And what you see here is kind of this wacky thing where they alternate these discount rates, right? The allocation. So some things really change. Now, we also have some results on, and we have various examples of this sort where kind of the optimal allocation doesn't exhibit these nice, well-ordered spreads. A general characterization is hard to establish, although we have some prescriptions for it. We can say various things. So for example, we did look at the general equilibrium benchmark for allocations, and there things behave much more nicely, but I didn't really talk about it in the talk, so I'll stop there.
So we have one more question. Rob?
Yes, there was a slide near the end that said, I think it was T2 equals T2 parentheses T1. Is that multiplication? What exactly did that mean?
Right, so recall that we have a supply constraint, right? And what I claimed is that we show you that the patient types, let me go to the slides, are served continuously between the T1 and T2. So it must be the case that here, I'll share the screen again. Right, so what I claimed is that the structure of the second best allocation is this one. Now, it must be the case that we have exactly the right supply between T1 and T2 to satisfy all of the patient agents, right? So that is exactly this constraint. So recall that the capital F here is the cumulative distribution function of the supply. So the left-hand side here is just the amount of supply that we have between T1 and T2. And that has to coincide with the mass of patient agents. So this implicitly defines T2 as a function of T1. So if you wanted to calculate the optimal second best allocation, essentially you have what I'm telling you is that you have 2 degrees of freedom, T1 and T3, because T2 will have to be fixed according to the feasibility.
Okay, yes, I see. So the first T2 is a time and the second T2 is a function. Got it, thank you.
Okay, do we have any more questions? Anybody wants to ask anything else? Well, I guess then, thanks again to Leeat.
There's one more question in the chat.
Is there? I'm missing. Yes, it just came in. Yaman, please.
Yes, thanks. I'm wondering, because you show this example with 2 equal measure types, but what if you have a measure of types are different? And is it true that the incentive problem for the type who has a large measure trivial because you report is your type is another type, then you will not be served? Is it true?
I don't think so. So the measure of types is going to affect the optimal allocation, but then incentive compatibility issues are going to remain. So, let me actually, I'll find the corresponding slides and I'll show you some comparative stat. I think it's a question about comparative statics effectively with respect to the type masses. So let me do this. And let's think about here. So, so if we think about this our optimal allocation here, right? So this is a situation where we're thinking, whoops, yeah. If we fix the overall mass of agents and we increase the mass of impatient agents, then naturally it's going to be easier to satisfy the condition of the lottery, right? So as you increase this thing, when we started if we started at the very low mass of impatient agents, you would not want to use a lottery. That wouldn't be incentive compatible at all. If you increase the impatient agents type, then you suddenly are more likely to hit the condition for the lottery, which you have a shot at it being incentive compatible. But the same sort of considerations are still going to hold. So I'm not sure I see kind of how they vanish.
So we got a couple more questions. Do we still have time to continue for the question and answer session? I believe we still have a few minutes, yes?
Yeah, but if we have very short answers, I'm sure it's fine, but...
well, there are two questions, one by Jean-Francois again and one by Alex Karpov. So Jean-Francois?
My question is, if I don't make mistake, you say that you normalize the utility at being served immediately across all individuals. So, but is this really innocuous?
Almost. So this relates to the objective function. So I put it under the rug. I said we weight people equally. So weighting them differently is almost like putting a different normalization at 0. Now, of course, if you put much more of a weight on the patient agents, if the patient agents had a much higher value of the good, then you might get a reversal of our results. You might actually want to serve them first under some conditions. As long as the weight is that you put is higher for the inpatient agents, so as long as the normalization is such that the inpatient agents get more weight effectively, then the results effectively go through. So that's a good point.
Okay, and one last question, I guess, Alex?
Yes, a short question about comparative statics. What happens if we shift the whole interval time allocation a bit later? And since we have different discount factors, the model, I think, is not invariant to this shift and something happens.
Absolutely right. You're absolutely right. Because essentially we'll want to multiply this function, right? So we'll want to multiply the function g of t by some value, right? By some by some constant, basically. And you'll want to do the same sort of exercise. So nothing will change in the characterization, the precise values might.
Okay, so thanks again for everybody. And let's have a break right now. Yes, I understand we have a break between the two talks. See you in 10 minutes. So we're back. Let's give it one more minute for everybody to walk back with their coffees. Okay. So should we be starting the second talk of today? This time it's one of our colleagues at ITAM in Mexico City, Tetsuya Hoshino. Tetsuya, please.
Hey, okay. Let me share my screen first. Okay. Do you see my screen? Okay,
Yes.
cool. Okay, thank you very much for organizing the COMSOC video seminar series. This is joint work with Enrique Oliveira at Penn State. You might have seen only my name on the website. This is because that he has joined this project later. He may answer the questions in the chat box. Okay. Oops. Yep. Sorry. Or there's some problem. Yep. Okay. Yep. First of all, I'd like to pose a trade-off about information acquisition. Information is beneficial because it will help us to make a better decision. But at the same time, our attention is scarce, which makes it costly to acquire information. For example, by reading the newspaper, you can learn about asset market, but at the same time, it takes time for you to read the newspapers. Hence, a decision maker endogenously chooses what and how much information to acquire, as well as when to acquire it. This trade-off is well captured by the framework of rational inattention. In this framework, decision maker acquires a costly information, costly signal about a payoff relevant state of nature before choosing an action. There are two features of rational inattention. The first is flexibility. Decision maker chooses the nature of information, that is, what information and how much, as well as when to acquire it. The second is optimization. Decision maker will maximize her expected sum of discounted payoff minus the information cost. Decision maker will maximize this object. Then a natural question is that how can we model this information cost? This is the question of ours. Our result is closely related to the recent influential work by Steiner, Stewart, and Matejka, 2017 Econometrica. Before I get to our result, let me talk about their work. To set up the model, I define a decision-making environment. Time is discrete, 1, 2, 3, blah, blah, blah. And there is a single agent who chooses an action every time. An environment E consists of the following components. The first is finite state space. State theta 1, theta 2, and so on are drawn according to a given prior pi. These states follow any stochastic process. They don't have to be IID or Markov. The second component is a finite action space A. The third is payoff functions U1, U2, and so on. Time t payoff depends on the entire history of states and actions, not only today's states and action, where the superscript t denotes the history up to time t. The fourth component is the discount factors, delta 1, delta 2, and so on, each of which is between 0 and 1. Delta superscript t with parentheses is the factor by which discount factor discounts the time t payoff. This form of discounting is more general than the usual exponential discounting, and it accommodates both finite and infinite time horizon models. For example, if delta 1 is 1, if delta 2 is also 1, but if delta 3 is 0, then this corresponds to a 2-period model. So this is the environment. Next, I'd like to define information acquisition. Decision maker can acquire information about the state, theta, before choosing an action. Her strategy consists of 2 components. The first, she chooses a custody signal xt about the state. Formally speaking, that she chooses a conditional distribution ft over a signal space x. The second component is that she observes a signal realization and then she chooses an action at. Formally speaking, that she chooses the mapping sigma t that maps the signal realizations to actions. These two are called information strategy and action strategy, respectively. I note that perfect recall is assumed. Decision maker knows all the past signals, x super t minus 1, at the beginning of time t. Also, in this presentation, I assume that decision maker does not observe the realized payoff, but this is just for simplicity. Now we can define the information cost. Among others, the most standard model in the literature is the entropy cost introduced by Christians. It is widely used because of its information theoretic foundation and, possibly more importantly, its tractability. Entropy H is a measure of uncertainty. Formally speaking, if we have a finite support random variable W, then the entropy H of W is defined as you now see here. Entropy reduction, so now I model the amount of information using entropy. Before you learn information, the uncertainty in terms of entropy should be high, but after you learn it, the uncertainty will be lower. Hence, this difference, entropy reduction, is a measure of the amount of information you have acquired. The entropy reduction, defined by this I function, is how much on average signal xt reduces the uncertainty about the states. This I function is called the mutual information in information theory. The entropy cost is just defined to be the linear function of this entropy reduction. That is, some positive constant lambda times the entropy reduction, mutual information, I. Since now we have an environment and the entropy cost, we can define the dynamic rational inattention problem. Decision maker chooses an information strategy F and action strategy sigma, so that she maximizes her expected sum of discounted payoff minus the entropy cost. This dynamic rational inattention problem can be simplified. There exists an optimal strategy with one-to-one mapping from signal realizations to actions. In other words, decision maker will choose a signal that directly corresponds to actions. Or in other words, decision maker will just acquire action recommendation as her signal. Formally speaking, we can replace the sigma of x with a super t, x super t with a super t, x super t minus 1 with a super t minus 1. In this simplified problem, decision maker chooses the conditional action distributions, PT, which I call choice rule. From now on, I will call this simplified problem the dynamic rational inattention problem. Steiner Student Taker have set up this problem, and they solved this dynamic rational inattention problem. They show that the optimal choice rule is a dynamic logic rule with bias toward an endogenous default rule. The conditional probability P is conditional probability P of choosing action A is proportional to Q times exponential of payoff terms over lambda. This rule is not exactly the same as the dynamic logic rule because of this Q term. This Q is called the default rule, which obtains as the marginal probability of choosing action AT. If, for example, QT is uniform over all actions, then this choice rule will be exactly the same as the logic rule. This term, payoff term, consists of today's utility UT plus discounted continuation value. So this VT is a value function. Then how can we define a value function? Steiner Student Taker also showed that the value function has the recursive and the log sum exponential form. For this recursivity, please note that you see VT on the left-hand side and the VT plus 1 on the right-hand side. This recursivity is quite important because it allows us to use the dynamic programming techniques. The recursivity is the root of destructibility, which leads to the explicit solution of dynamic logic-like form. In other words, the recursivity means that the dynamic rational inattention problem can be reduced to a collection of a static rational inattention problem. Here is a one-line summary of one of the key results of a Steiner Student Taker. The entropy cost makes the value function of every environment recursive. Then a natural question that arises is, are there any other cost functions that make the value function recursive? In other words, what costs make the value function of every environment recursive? When can we use dynamic programming? In other words, here is our answer. Only the entropy cost function makes the value function of every environment recursive. Only the entropy. Let me rephrase these results of a Steiner Student Taker in ours. If the cost function is entropic, then the value function of every environment is recursive, according to Steiner Student Taker. Our result corresponds to the converse, with additional assumptions, as we will now see. At this stage, I just want to say that I define the recursivity using an abstract Bellman equations, and I do not assume the log sum exponential form. So this equivalence is our main result. To better understand the result, let us take a look at it. Let's take a closer look at it. First, I define an environment E in the same manner as before. Here I reproduce the definition. Finite state space with a prior, action space, payoff functions, and discount factors. Next, I'm going to define a non-parametric cost function. For any finite support random variable W and W prime, a cost function C is defined such that it is non-negative, bounded, continuous, and convex. It is also Blackwell monotone. That is, the better information that brings more expected payoff to you is more costly. This is necessary to capture the trade-off of information acquisition. I also require that cost of acquiring no information be 0. More formally speaking, that if A is an independent signal of W, given W prime, then the cost of such an uninformative signal must be 0. The entropy cost satisfies all these properties, and thus the C function is a generalization of the entropy cost. For fixed cost C, and I define a dynamic rational inattention problem of environment E, as you now see. It is not difficult to see that this dynamic rational inattention problem has an optimal choice rule. So existence of a solution is guaranteed. Then the next step is then how can we define the value of the given environment E with a fixed cost function C? The first, I represent environment E using some random variable st, and then I define the value functional V as a mapping from the random variable to the continuation value of the environment E. I will explain later that why I take this unusual approach. Let me talk about the first step. For fixed cost function C, the dynamic rational inattention problem of a given environment E is as follows, as we have just defined. Then we know that the optimal choice rule exists. Then we define an optimal default rule Q as the marginal distribution of actions, which obtains by integrating out states from the optimal choice rule P. If action AT is distributed according to this Q, then it is independent of states conditional on the parsed actions. For a given environment E with an optimal default rule Q, which we have just defined, an induced random variable given history is defined as you now see, as the sum of discounted random payoffs. Here I note that the state theta is distributed according to a given prior pi, and actions is distributed according to an optimal default rule Q. I emphasize there is no expectations here, so ST is just a random variable, not the value. I also want to say that the payoffs are evaluated in terms of a time t values. Now I define a value function V as a mapping such that for each random variable ST and for any history of states and actions, then the value functional of S is just to maximize the continuation value given the history. It can be formalized as follows. So maximization of the continuation values with some constraint. This constraint requires that, this requires constraint that the control variable P must be a martingale spread of the given default rule Q. This is a bit notationally heavy, but you don't have to worry about this notation. This value function just is a mapping from the induced random variable to the optimized continuation value. Now we have reached the key concept, recursivity. This is one of the reasons that why we have introduced the random variable representation of the environment. For random variable S and a history of states and actions, I define the recursivity using this Bellman-Lukin equation. The left-hand side is the value of a dynamic rational inattention problem, as we have just defined. The right-hand side is the value of the corresponding static rational inattention problem. In this static environment, the decision maker will be just choosing an action once and for all, and her payoff is equal to her time t payoff plus the discounted continuation value. This Bellman equation says that a dynamic rational inattention problem is reduced to a static rational inattention problem. This is the value of them. reduce the static rational intention problem. Okay. Our main result also requires 2 additional assumptions. The first is the monotonicity of the value function. Consider 2 random variables corresponding to 2 environments, S hat corresponding to E and E hat. If they are ranked according to the first order stochastic dominance, then their values are also ranked in that order. The second is a regularity assumption. I'm going to restrict our attention to environments where I have interior choice, optimal choice rules. Interior in the sense that all the actions have a stricter positive probabilities. But this assumption is just for simplicity. I'm pretty sure that we can dispense with it. So now we can state our result formally. If a value function V is recursive, then there exists a time-independent constant lambda, such that for any environment E and for any histories of actions A super T minus 1, then the cost of signal AT must be given in the entropy way. So this is the main result. So yeah, actually this is all. So thank you very much for your attention. So yeah, so I want to keep this the kind of summary slide for a last minute. So yeah, so because of the time and because of this bit technicality, so it's a bit difficult for me to give you the proof ideas, but this is the main result of our research. Thank you very much. If you have any questions, I'm happy to answer them.
Do we have any questions? Is there anything on the chat? Doesn't appear. Anybody wants to ask a question? Hello? Okay. So in that case.
Okay, yeah.
Yes, any questions? Okay, in that case, so I guess I would just like to thank our speakers today. And definitely thank the COMSOC for allowing us to advertise that the social choice and welfare is still around. So next year we expect the full-blown Congress. We expect Leeat as a plenary speaker. So please apply. So we're trying to coordinate with COMSOC that there is no conflict on attendance. So we will, given the difficulties of the situation, try to arrange some broadcasts, at least of the plenary talks, and maybe even allow for some long distance presentations, because we understand that even if travel mostly resumes, there may be hiccups. But we still have full intention of running a normal presential conference next June. So thank you very much, and let me yield the floor to the organizers of COMSOC.
Thanks. So thanks, Andrei, for organizing social choice and welfare workshop, not just once, but twice. Right? This is a tremendous effort if you do it just once. Kind of volunteering to do it the second time around is just amazing. So I just wanted to say a couple of words about the next week's seminar. So next week, we have 2 speakers who are very well recognized in computational social choice community. This is Jerome Lang and our own Ulle Endres. So this is, okay, so I wouldn't say necessarily this is intentional. It's more like this is just happened to be this combination, but to me it's a very meaningful combination because Ulle and Jerome were the organizers of the very first COMSOC workshop in Amsterdam in 2006, which effectively served as a birthplace of the entire research field, kind of the computer science angle on social choice. So that was an important event for our community. So that was, for me, I suppose, an entry point into the field, right? And it's wonderful to have both of them, both excellent speakers, speaking at the seminar next week. Okay, that's all from me. Okay, so in case we don't have any further comments, suggestions, so I guess we'll keep the chat open for a little bit longer so that, you know, people can exchange opinions. But kind of overall, this is the end of the seminar, today's seminar. Thanks, everyone.